On the bench today is a Line 6 DuoVerb. The report with this particular amplifier is that it is intermittent. The gentleman that owns this particular amplifier happens to be my chiropractor and friend, Nevin Grushka. He's out of Coconut Creek, Florida. Awesome chiropractor, by the way. Keeps me quite healthy. I guess him and his brother, as it turns out, own a studio somewhere down here in Florida, and this is one of the heads they have to offer their customers. They're getting some reports back from the customers in the recording studio that it has an intermittent problem. However, they're unsure whether it's in the signal path, the power supply, so they couldn't give me too many details. Nonetheless, doesn't matter. We will make it work again, and we will discover what that issue is. So this is a Line 6 DuoVerb. It comes in the early days of Line 6 that I'm aware of, with a little bit of research that I did when Line 6 was first starting to make heads. And some people love this amplifier and think it's just dynamite, and some people, because I guess there are some issues with these, are looking for answers on how to service them. So hopefully we can provide that in this video here. So going through the front side of the amplifier, we can see that it's really built well like a tank here. It's very solid. It has one input here, a modeling section that, from what I understand, in general modeling, they take individual amplifiers and they record a sound of that amplifier and they put it as a base, as a model, and then they give you the functionality to be able to do and shape that sound how you'd like it, as if that model of amp were actually sitting in front of you, and these were your choices that were common to all of these particular amplifiers. There's two sections here. You can see amp 1 or amp 2. Not sure if that is supposed to return to center or not. Maybe it is. Interesting feeling switch. All right, I guess they both do that. That must be a Line 6 thing. I would have suspected it would have stayed on one or stayed on the other. Nonetheless, looks like we have drive section, bass, mid, treble, presence, volume, and reverb. All very standard, and a master volume here. Very standard to most heads. So at any rate, it looks like a nice clear jewel here, and a power switch. So very simple on the front. Looks like these are probably presets perhaps that you can make if you're out gigging. You can maybe select an amplifier, make a tone, set it, and I believe you can assign those to those particular buttons and then recall them either by a foot switch or by pressing the button themselves. Seems like a Line 6 thing. So let's look at the top here. Oh, look, there's a sticker for Nevin. Great chiropractor, by the way. Nice handle here, again, very solid. Let's turn her around and see what we got at the bottom. And the back, looks like the bottom, good, looks solid. On the back here, we have an IEC cable input up for 120 volts. And that's just operating voltage, 100 to 120 at 50 or 60 hertz, 250 watts maximum. Looks like here we have 2 right out, 2 left out, or mono out for speaker outs. And we have an output impedance switch, 4 ohms or 8 ohms consecutively. Looks like somebody was running this at a 4 ohm load. We've got cabinet modeling, off, open, or closed. That's interesting. So we'll have to check out what that is. And then, of course, headphones. This looks like a pedal. Must be a Line 6 pedal you can put in there that can give you some more additional functionality perhaps with this amp. Looks like we got a MIDI in, MIDI out effects loop here, or loop of some sort. Here's an effects loop, an actual one, it looks like. Left, right, send and return, pretty normal stuff. Trim level, and this is an interesting XLR out, so I suppose you could go direct with this amp, say, to a board, or maybe not even to speakers, maybe right direct to front of house perhaps if you're gigging in a club. And then of course a ground lift. So all pretty straightforward. I'm going to go ahead and pull this chassis out. It looks to me like most heads. There's 4 screws here. I'll pull these out. We'll get the chassis on the bench. We'll take a look inside. So before we actually take the chassis out of the head and take a look at what's happening inside, I thought we would at least fire it up and do so slowly. So I've got it hooked up to my variac and current limited power supply, and I'm going to just bring it up slowly. I know it's not a tube amp, and you may even think, well, why does he have a dummy load on it? I just do those sorts of things all the time, anytime I'm working on a solid state amp or a tube amp. And I know a lot of you tech guys are out there that are saying, oh, you don't need that on a solid state amp. And mostly you're right. But if this thing were pegged on the inside, let's say that we see this master volumes down, but if it actually had a problem and somewhere in the circuit it was pegged before the output and it was sending maximum output, a cautionary tale would be to just fire it up with a dummy load. Better safe than sorry. So what I'm going to do is I'm going to just turn on the power switch here, and I'm going to start turning up my variac. Let's see, we're at 50 volts, 60 volts. See if we start to get any activity. Nothing on my bulbs yet, so that's good. 70 volts. Let me see, can I see anything happening with any lights? Nothing yet. Keep going here. We're at 94, 98, 100 volts. Let's see if we have anything yet. Oh, I got a little bit of a flicker happening inside that, 100 volts. Let's keep going. Let me try to get her up to 110. 120 volts. Let's see what we can get. Right here. 120 volts. Still have a flickering inside, so that tells me that there's something going on definitely in the power section. I also started seeing some flickering on the bulb on my variac. So my guess is, or my current limited power supply rather, my guess is obviously this is more than just an intermittent problem. Definitely something in the power section if we're seeing something's trying to turn on and then it's not being able to do so. Let's see if you guys can actually see that a little bit better. I'll try to bring this in a little bit more. See that? It's trying to turn on and trying to stay on. So I'm glad I have a dummy load on it at the moment. Again, we don't know the current issue, but we will figure it out. Next shot. So if you're taking one of these apart and you're working on them, you can take a look here that this is the chassis that came out of that head. And there are 4 screws on the back, and then 4 more screws on the front that will actually separate this chassis. I don't know if you can see that there's 2 separate pieces, right? Let's try to back that out. Yeah, there's 2 separate pieces. One piece of metal here that turns 90, and then another piece of metal here that comprises the entire chassis. Additionally, if you're taking the chassis out of the head, the handle screws are part of what holds that chassis into the head. So you have to take those 4 screws out as well as the 4 screws in the corners. All right, once those 8 screws are out, you can see the top of the chassis lifts off in this fashion. And if I tilt it up a little bit more, you'll see that there are a series of wires that connect one side to the other. Here we have a ribbon strip, and here we have a bundle of wires. It looks like a 1, 2, 3, 4, 5 pin connector there, and then we have a power switch here. So I'm going to go ahead and remove everything from just one side of the chassis. So I'll remove everything from this side, and then we'll be right back. On second thought, what I've decided to do is we're going to remove these 2 power switch cables here and kind of slide this underneath the other portion of the chassis just so they can rest and I can still have everything exposed to me without having to take these off just for the moment while we do initial troubleshooting. Again, I'm going to instantly start reaching toward the power section before I get into anything beyond that. So that's going to be isolated. Let me grab something to point with here. You can see this portion. Let me zoom in a little bit. You can see this portion of the power supply. And by first glance here, you can see this separation. The power amp side to the secondary side board for the power supply. Here we can see we have the output section, and then we have a plethora of boards and chips for the DSP section. Looks pretty well built though. I don't see anything real obvious. I don't see anything burnt out. I'm going to suspect these caps probably. This thing is over 20 years old, so maybe those caps have started to go bad. We will figure that out. I found this kind of interesting right here. It says, warning, do not operate without proper loads on all outputs. I guess that backs up my theory a little bit for the solid state, powering up without a dummy load. Again, that's a separate idea. At any rate, manufacturer felt it was important enough to talk about that as well. Also can see this is August 2002, and looks like it was made in Malaysia. At least this particular board was. So that gives us an idea as to how old this puppy is. So in troubleshooting this on a basic sense, just to find out if it's something simple or not before I pull out the schematic and really dive in, I'll just take care of some obvious, answer some obvious questions. One of the things is we know that the power coming into this unit is intermittent, and it has a pulsating factor to it. We shouldn't have a pulsating factor at this point though. So if I take out this, let me unplug this here. If I take out this connector here that's next to the bridge rectifier, and that pulls the power away from this portion of the power supply, and this section here is isolated, if the problem is in that section, when I check it at, well, let's see, let's pull this off too. When I check it at these 2 points here, I should have a solid 120 something volts. Let me put my AC meter on AC here, or my multimeter on AC. Let's see what we're getting at this point here. All right, so we got a solid 124 volts coming in, and that little bit of fluctuation you're seeing there is just local line voltage. Other houses around me and other parts in my home, I think the wife's got the washer going, so at any rate, that section looks good. Just again, quick troubleshooting, trying to find out the problem without spending out too much time, if it's going to be a simple problem, but we'll find out. So what I'm going to do next is I'm going to pull this board. I don't believe it's here. I believe that the issue is somewhere here. So it looks like I have to take out these 3. Yeah, okay, 1, 2, 3 connectors. So it looks like we have a 6-pin connector here. Oh, it's the squeeze style, I think. So if you grab that, squeeze, maybe. Oh, all right, fine. Yeah, 6-pin connector here. So if you're working on one of these and you're following along, you can see that that's how you do. You just squeeze that little guy there, pull it out. Looks like we've got a 1, 2, 3, 4, 6, 7, 8-pin connector here. Oh, that one came out rather easy. Same thing. You can see the side profile there. I'll zoom in a little bit. And you can see that if you squeeze this side versus that side, that's how that connector is able to come out of there. All right, so this ribbon connector, you got to be careful with all ribbon connectors, because typically, most of the time, there could be hard wire or braided wire inside, and they don't like to be bent a whole lot or twisted too much. So this style, I believe you just pull up on, yeah. So nothing to pinch or squeeze, just straight pull in, pull out of the socket. So that disconnects me from those 3 parts. Now we've got 1, 2, 3, 4, 5, 6, looks like 7 screws to take out. Then that should pull this, I should be able to pull that board out, and then we can start checking the component level from there. All right, I have the actual screws pulled out of there, so I should be able now to pull this guy out. We'll do it together. Great. Okay. Well, now we can see that there's not necessarily anything that's a telltale sign right away. I don't really see any burnt traces, or I don't see any leaking fluid from any electrolytic caps. Now, although that is a little bit suspect there. Can you see that? Let's see if I can get a little light. Where is my flashlight? Can you see that, what looks like moisture there? Right on the end, right there. Huh. I wonder if that is leaking caps. Let's look at the other side. No, those are just resistors, so that might actually be from heat. Yeah, but regardless, it doesn't look like it's fluid, so that's probably just from heat. At any rate, something to be cautious of here is even though I pulled this board, these caps, in fact, all of these electrolytic caps that look like this, they can actually still have charge on them. So because the board is fashioned in the chassis here, I really can't go through and discharge those. So if you're pulling this out, you need to be very careful to realize that some of these bigger caps, and even these smaller ones, they can hurt you as well, can still have charge on them, and they can give you one heck of a shock. So what I'm going to do is carefully take this board, place it off, and the way I do that is in this case, I'll take this and I'll put it down on something like this, like a cloth, set it off to the side, clear my bench, and then I'll go through and I'll discharge those caps. So something else I wanted to just mention real quick is the obvious, really well build that Line 6 puts into a lot of their products. The quality seems to be quite good. All of these capacitors are actually Nichicon, which is a great brand name, Japanese, well-made capacitor, and not cheap by any means. So because this is 2002, the chances of these capacitors being bad in, 18 or 19 years, depending on how much time is on this unit, and it doesn't look like perhaps there is that much, I would be doubtful that a lot of these caps are bad, but we could pull a few and we could check them, check the ESR values, and see what what we're up against. But just generally, if this were maybe 25 years old or so, and they were not name brand caps, then you're probably looking at doing a full recap. Even if it came into service, you could have leaking caps, because these are actually sealed with silicone to prevent the traces from breaking through vibration, which is a sign of quality that Line 6 decided to put into their builds. You can't necessarily see if there is any electrolytes coming from or any juices basically of the capacitor leaking out. But that is two different kinds, right? You've got a physical leakage, but that has nothing to do with being leaky in an ESR equivalent series resistance kind of fashion. So two different topics. But at any rate, it's just nice to see that they took the time to do that, because a lot of, here I'll bring the camera in a little bit closer, a lot of components that you look at nowadays, or for this particular build, why they put that silicone is, like, if you look at the size of this capacitor, it's kind of beefy, and you can see the leads are kind of pretty thick, and it's because it has some weight to it, any vibration through these heavier leads can actually tear the copper off the circuit board, if it's just a single side and maybe doesn't have a through hole via, to really put a lot of solder on it and keep it solid. So the silicone helps to keep that item in place, as to where something small like this, you can see, has still kind of, in fact, in ratio, these leads are actually thicker for the size body there than these are for this. The holding power, because this is a much lighter component, the stresses that will happen laterally through vibration are so much less. So you see that they didn't put any, let's see if I can go right here, through this small capacitor here, or this one here, you can see that they didn't put any silicone, because they are smaller. Additionally, they're not going to put silicone because you have all of these small surface mounted pieces in close proximity to the capacitors themselves. And in doing so, they're kind of shooting themselves in the foot, because if they did, it makes it really difficult, because caps have to be replaced from time to time. They are a wear item. They do go out. They are designed to be replaced. And putting silicone next to small surface mount components, you're just asking for a lot of mess and trouble in trying to get the silicone out and service if you have to replace other small components. So they don't typically put it on very small ones like this, just the larger items that you see here. So here we have another part of the amplifier. Let me pull this out and back this in center so you guys can see the entire chassis here. So here's the entire chassis. Here we have a motherboard portion of the chassis that has the main processor for the unit. Here we have the output portion that's responsible for driving the speaker load. There are the two transistors that sit and are attached to this large heatsink that's back here. Now it looks like there's maybe a mica spacer in there. I'm not sure if that's mica, if they use that nowadays or not, but that's what I'm used to seeing. And there's some components on here that we have to update according to some of the research that I've done, some of the problems that are with these units. And I'll share that with you shortly once I get this out. Now, in order to remove this, you have to take off, and this is going to be an Allen wrench to use here and here. You have to take the pressure off of these portions. There's one down here as well. At that point, this should slide off. You can see that I've color-coded the connectors here, right? So even though, you know, common sense would say that's a 5-pin connector, that's a 6-pin connector, how can you screw that up? But you wouldn't believe the amount of times when you get really deep into something and you got to try to trace out. Well, that takes the thought out of it. So I just put a little blue on there, a little red on there, and that you get a little bit closer. That just makes it easy for me when I assemble it back together. And if I want to get that off there, I just take a little bit of paper towel and some isopropyl rubbing alcohol and boom, right off. Actually, denatured alcohol is even better, dissolves that stuff like not a problem. So at any rate, let me get this small board out of here and we'll go from there. As it turns out, these are 9/64ths. So if you're working on one of these, use the appropriate Allen wrench not to strip out those fasteners. 9/64ths. So, you know, in fact, those are really on there tight and sealed with that thermal paste. So rather than break that seal, I don't see any overheating indications. So why don't we just go ahead, we'll take the entire heat sink out. Now there's 2 screws here, and then there's additional 2 screws here on the bottom. And we'll just remove it. The reason I need to do that is I need access to the bottom of the board to replace these parts. So I'll just do that off camera. I'll take these 4 screws, we'll come back, we'll see the board with the heatsink. So here we have the technical bulletin number 022. Now, I don't believe that this is public knowledge, or at least wasn't for a specific period of time. I believe that time is now beyond and is no longer a concern. So with that being said, this particular thing talks about to lower the cutoff frequency of the power amp to eliminate the possibility of oscillation. So when we turned that amp on, we could see that it was oscillating just by the power amp turning on and turning off every few seconds. So I don't know if this is going to alleviate that problem, but regardless, because this is a technical bulletin for the DuoVerb HD head, which is what we have, it indicates here that we should replace R5 and R6, which are the 2.2 ohm 2-watt resistors, with a 2.2 ohm 3-watt resistor, which we have now, and C7 and C9 to go from a 0.1 microfarad 100 volt polycap to a 0.56 100 volt polycap. We have those as well. So where does this apply? This applies on this smaller daughter board that we talked about a little earlier. So let me get down here to show you. So the indication was R5 and R6. So R5 is here, so we'll replace this one. And R6 is here, so we'll replace this one. Additionally, they're looking for C7 and C9. That's this guy here. This is C7, and then this is C9. Well, finally, after 2 weeks of waiting, because it's COVID right now, everything is slow. People in their companies are undermanned, and that's not a problem. The customer didn't mind. So, but after a few weeks of waiting, we finally got the DigiKey order in, so let's see what we got here. So here's the 3-watt resistors that we're looking to replace. And wonderful. Great, so these guys are in. And what do we have here? Actually, let's take that back. These are the 3-watt resistors. And these are the 1/2 watt resistor. You know, I just think about the size difference there, you can see. All right, so that's good. all of our electrolytic caps that we're going to go ahead and update and replace. And these are, I believe, I can't see, but I think that they are Nichikan. All right, so really high quality caps going back into that high quality unit. And these are our, you probably can't see that, but those are our Zener diodes that we're looking to replace. We've got some poly caps, more electrolytics, and these are also, let's take a look, hopefully, yes, Nichikan, and some more polys. And here we have some of the diodes, the surface mount diodes. Great, so it's all in. Let's get to it. All right, so all those parts have been replaced and put in with better quality parts than came from the factory. And now what I'll do is just go through and snip these bottom leads all the way through here. I like to use this particular tool. It's I think it's Austrian or maybe German. I probably picked these up when I was there. Oh, Germany, yeah. Picked these up when I was in Austria. At any rate, just go through here, and I don't clip the solder itself, so I get up flush and then come down just a hair. I leave a little bit of lead in places where I have the room to do so. Beautiful. Here in the output section of the two ICs that are, I believe it or not, glued on to this heatsink. Some manufacturers do that. I'm going to have a problem getting those off. I've ordered two ICs. I see some anomalies between them, and I don't really have a way to test them in circuit other than to each other, and they're not the same. There's a small problem. Beyond that, there's also an additional problem with two of the resistor arrays here. You have one here and one here. Now, both of these are 20 kilo ohm rated, but if you go pin to pin, they should be 10. Yeah, so there's 10. And if we go all the way down to the next pin, 10. So that's accurate. Getting to this end, 10. Now, same thing here, should be all the way down. However, if I come to the very end of this one, we see we get 2.6. Even though it's climbing down, there's a cap in that. But anyway, regardless, 2.6. So these first two rows are 2.6. This third row is 10. And then everything else is 10 down. All right, so what I was trying to talk about earlier is if I go from the case of the IC to pin 11, which is here, I got 30 ohms on this one. And if I go to this one, got 256. Conversely, if I go to 12 on this pin, I've got 32. And when I come 12 to this pin, or this IC, I've got 100 and, well, it's floating again because of that cap. But you can see the difference that's in there. So I'm really not going to know if these are good ICs until the new ones come in. And then what I'm going to do is I'm going to put them on my curve tracer, and I'm going to compare a new IC to each one of these. So as we can see here, I have a large task ahead of me. These TDA7293s are reading differently, and they should be identical. Now, to get these out of here is a little bit of a task. So first off, this bolt has to come out, and these are actually glued in. So I'm going to have to gently and carefully, hopefully not damage this transfer material here, or I'll have to replace it, maybe with some mica and some thermal paste, of course. But to get these pins out of here are going to be quite a problem. And since these are expensive chips, hopefully not both of them are bad, but I have two replacements coming in. But of course, I don't know the values of these chips. You can't just test them in circuit, so I have to test them outside of the circuit. So what I've done is I took let me zoom in on this a little bit. I made these guys. So what these are is from a circuit PCB printing board software, and I made these in that design. So what'll happen is I'm going to take the new IC that's coming in. I'm going to populate it here, and I'm going to populate some pins on this side, and we're going to look at a new IC compared to these older two, and we're going to see if either one of them is good, or if they're both bad, or how they compare to a new IC on my curve tracer system. And here you can see where I used the software called DipTrace to make my little circuit boards here, but that's where it came from. I just designed it, made the traces, and filled it in. But I was able to choose the component, which is neat. Well, as it turns out, HP is no longer making the paper that I used to use, which was their premium gloss paper, and they have discontinued it. So I just randomly chose this off the net, another Amazon, and I'll let you know how it works. Hopefully it's going to be good. So what we want to do here is degrease this puppy. Now I'm out of degreaser at the moment, so once again I'm using contact cleaner. So just spray a little bit on there, wipe it off, and that is going to help to not let anything really that's deep down in those cells get transferred further when I sand this, because I'm going to have to sand it so it has a little bit of texture to it, so we get the best adhesion. So it wasn't too bad, so I think that's good enough for now. So now lots of people use different grits. My preference is 800, but fresh, brand new 800. See, when I made these, I buffed it up a little bit because I have the actual hole size that the hole needs to be. But a little trick I learned is making the hole size a lot smaller. Then when the drill goes in to guide itself, even though it's bigger, it will get to the very center. The copper will pull it into that pad as long as the paper's out of the way. So sometimes I just got to, on these small boards, I go this direction, or I put them in there and do it with the unit off itself. So now I'll just take it, put it in some fresh water, let it soak for a little while, and then that'll peel off rather easy, hopefully. Actually, you can almost watch it impregnate with water there. Kind of did that all on its own. Now, if I'm real lucky, that's going to be stuck to the copper. The ink is. Look at that. How often does that happen? It doesn't. That is amazing results with that paper. That is the best results I have ever had when it comes to making your own PCBs. I just can't believe that. That just literally came off by itself. Come across here and separate these guys just by eye. Be good enough. Don't like to bend toward the copper. I find that's not the best. I bend toward the, if there's a single-sided board, bend toward the other side. Just that easy. All right, now this is a process of etching by ferric chloride. So do yourself a favor and wear gloves, and don't be in an area where if you spill something, you spill the product itself, you're not gonna regret getting it on some things that perhaps you didn't want to. So this is a very light mixture, and don't need a lot. Got two small boards here, right? So that's actually going to be reusable. I'll pour that back in the bottle when I'm done. So I'm going to just put these inside here like so. So now what I'll do is just put this puppy back on. And then I'll bring this downstairs and I'll heat it just a little bit, and I'll agitate it like this for just a few minutes, and then we'll be back. All right, so I've been agitating this for about 9 minutes now, and I took it down, applied a little heat on it, and you notice that it's darker now in color, right? So darker compared to the brand new ferric chloride. That's just the reaction of the copper. So let's take a look at what we got here. And again, you got to be real careful to see. Now this is a little bit harder product to see because it's brown already. So what I'll do here is take a little paper towel, try to get a sense whether or not I have copper left on there. And I do. You can see just a little bit in the center. So we're almost there, but not quite. All right, so as it turns out, we are out of acetone. So I conferred with my better half, and she's offered up this product. So we're gonna see what happens here. All right, a last ditch effort. Otherwise, this will have to wait till I get to Home Depot or somewhere to get some more lacquer thinner. This is Moz polish, metal polish. I'm reaching now just to see. Well, a whole lot of elbow grease later, you can see how many, how much this Moz actually did do the job. Took a lot longer than I would have really wanted. Let me get some more light on this here. But that's generically acceptable for the moment. And again, very popular method on the internet. Lots of people doing this. I actually learned this from another website. Liquid tin. So you just pour a little bit in. And just enough to cover the item. Probably not the most ideal use. But put it over the top, and you can slowly see it. If I can, you can see the copper turn to a silver color. And what that's doing is that is actually, believe it or not, it's truly tinning that copper through chemical reaction. And now on to one of my other favorite tools, the Dremel drill press. Put your Dremel in there, choose your drill size for your product, drill away, wearing eye protection. And in this case, looks like 80 millimeters will do. 43 that way, that doesn't really matter. This way, so I'll choose an 80. All right, so if I've got a little bit of luck on my side, this will have worked out. So what I'm going to do now is I'll flip the board over, and these headers will go on this side. Ah, nice fit. Drops in relatively good. I'll bring that up to the camera. Yeah, that looks pretty good. So I'll put one header there, the other header here. Then when this ICs arrive, and then when I have a chance to pull the other ones out of the amp, you'll see how they sit in there, and they're offset by half a tick. At any rate, this portion will actually go down as well. Let's see if how good I did. And then we'll just go on down since I'm right-handed, I'll go away. Good to go. And so, all right, pin 1, pin 2, pin 3. So what I've done here is I have created this little jig, basically, so I can get the 15 pins of the TDA7293 into my curve tracer. And I'll turn my scope on here. So basically, let me lift this up. What's happening is I am just going to use pins 20 through pin 6 in a reverse fashion because I made the board a little bit too big. I'm going to stick it inside of here and close that. Now both of these that are sitting in here, both of these chips are brand new. So I'm just curious what two brand new chips look like. Are they matched? Do they need to be matched? How close are they? So because pin 1 on either chip is the common, I'm here in pin 20. Again, I'm just using it in reverse. Just easier to sit in there rather than this little bar would be in the way. I guess I didn't think about that when I made this jig. So nonetheless, so I'm going to go through and we're going to look at the residue patterns of each one of these compared to signal ground. And of course we would expect a short there, fine. Pin 1 to 2 and we can see that it looks like something like a Zener diode. And let's go 1 to 3, almost the same thing. And the flip-flop is happening left to right, so that's reference test. So left chip, right chip, left chip, right chip. Pin 4, same thing. Left chip, right chip. Pin 5, same thing. Pin 6. Now you can see a little bit of movement, but they're almost identical. Pretty good. So that's left chip, right chip. Now there you're starting to see a little bit of movement. Oh, that might actually be my finger on the switch. I think it is actually. But again, almost identical. This is what the listen-to pattern for pin 7 looks like. Pin 8. Now here you can see a little bit of a, let me get something to point with here. So you can see a little bit of movement happening here, left to right. This left, right, left, right. So they're comparing the two. So this is indicative of a capacitor that must be in line maybe with a diode internally on that chip. Not sure what that circuit looks like. Let's move on. 9, almost the same thing. Looks like a diode. 10, same thing, left, right, left, right. 11, slight variance here. 12, same kind of thing, right? So one's a little bit less. 13, that's an interesting pattern, but again, close enough too, right? 14, and finally 15. So one important thing to notice on here is, if you guys are going to work on one of these, is in certain circuits, the body of the TDA7293 is actually connected to ground, and sometimes it's not. So in this case, it's not. So I'll even go here on the non-black anodized. You can see that neither body, but now connected together, they are. Alright, so it looks like just using a flat razor coming at it is what's I was able to release this side. So I'm going underneath the silicone wafer and just kind of going in. It must just be stuck through heat throughout time. There we go. Now she's released. So no glue, just natural adhesion over time. And just while I'm at it, I was trying to see what was connected to the bodies of these. I'm going to put this on the body of the left one. And we'll see that 1, 2, 3, 4, well, we'll just go through. 1, 2, 3, 4, 5, 6, 7. 7 and 8. And as we can see, this is the pinout for that particular IC. Pin 8 is the negative VS here, signal. So we do have a normal standby ground here on pin 1, but that's not connected to the body in any way. Apparently pin 8 is connected to the body. That's obviously by design, right? Alright, so these are going to be a bear for me to get out. As you can see, that's a lot of pins in there. That's 15 pins per side. I do have access to the bottom, of course. And I'll take a different approach than some, two-part approach. Because many of these are on through-hole vias, I'm really going to try to get it out with as much least amount of damage possible, so we can test these puppies and see what the failure point was. So the way I'll do that is I'm going to actually add a little bit of solder to each individual pin directly. Let's see if you can see what I'm doing here. Right. I'm just going to add a little touch of solder, kind of wake them up in a sense, right? That solder adds a little bit of the rosin flux that's already inside the new solder as well. Just a touch, just to wake them up. Believe it or not, adding a little bit of solder will allow for easier removal. Now if we look at the other side, you can see that there's some of those that have gone through and some that have not. Just from the factory, of course, initial soldering, and what I'm doing here. So I'm going to go for this first row of pins, and I'm going to do this guy right here. So this is a solder sucking machine, and I've got it set to 850 right now, but these are long pins, so that should be good. I put a brand new tip on there. There we go. Got a brand new tip on there, brand new filtered screen inside there. Should be clean and ready to rock. So we'll see. So I'm gonna put it on there so there's enough dwell time to get to the top side and round that puppy off. All right, so that'll do that. Now, I suspect that you know, I've got as much out of there as possible, but I don't know if these pins are going to be loose or not. So I'm going to just try to push one through here and see. Yeah, I'm going to then transition from having the majority, and now I'm going to add some flux to all of them, and I'm going to use this, which will actually wick it right off the pins. Oh, well. That was a little easier than I thought. So I'm just gonna put a little pressure, maybe rock it around a little bit. Oh. Woohoo! So we have the same test environment set up here. To the left we have our brand new reference chip, and to the right we have the channel right chip out of the line 6. So we're going to start with pin 1 and work our way down. So pin 1 is reference test, reference test. So that looks good. Pin 2 is reference test, reference test, reference test. So a little different there. Pin 3 is reference test, a lot different. So reference test. I'm going to have to tell you which one they are as we're here, because you can't see the flip-flopping LEDs below. So reference test, reference test. So that number is different. 4, almost the same, reference test, reference test. 5, identical, good. 6, oh, look at that, reference test, good, bad, good, bad. Shorted on pin 6, pin 7, also shorted on pin 7, so we got reference test, good, bad. Pin 8, wow, this IC is just messed up, isn't it? So reference test, good, bad. Pin 9, that looks good to go on both sides. Pin 10, little variation, but still acceptable. Pin 11, another short, reference test, good, bad. 12, reference test, good, bad. 13, reference test, good, bad, 14, same thing, reference test, good, bad. Finally 15, oh boy, reference test, good, bad. So you can see the obvious problems there. This IC is all jacked up. So let's put the next one on, and that will be the left side. Where are we at? The left side IC from line 6. We'll be back. Okay, here we go. So we're going to do the left side IC of this line 6, starting with pin 1. It's good on both sides. Pin 2, slight variation there, but still good on both sides. Pin 3, slight variation, good on both sides. Pin 4, so I guess that's a slight variation, but you know, these, who knows when these ICs were made, you know, decades apart, right? Pin 5, pretty close. Pin 6. Wow, pin 6 is an obvious difference. So this is reference on the left, reference test, reference test. So the good one, the old one, the new one, the old one. Pin 7. I didn't think we'd see problems with this IC, but very interesting. There's pin 7. You can see there's an obvious short there. Pin 8. Wow, so let's go back to 7. So I'll tell you, this is reference test, good, bad, good, bad. Pin 8, this is good, bad, reference test, reference shorted. Pin 9, now this is very interesting. They both diodes, but they look like different diodes. Alright, so this is 9, so this is reference test, good, bad. Pin 10, so we got reference test. I want to make sure I got these in the right sockets. Alright, pin 11. Alright, so pin 10, sorry. So this is reference test for pin 10. Pin 11, reference test. So this is also a shorter one. Pin 12, quite different. Reference test. Pin 13 is shorted, so we got reference test. Pin 14, reference test. Pin 15, reference test. Alright, well, just for the sake of fun here, I thought we might as well put them against each other, the two old ones, and see what this amp was seeing by the time the switch mode power supply started having the return blinking problem. So this is chip on the left, that's the left side, and on the right, that's the right side. We'll start with pin 1. So pin 1 on all of them is ground, so that's correct. Pin 2, that looks good between these two ICs. Pin 3, you can see there's an obvious difference there. Pin 4, slight difference there. Pin 5, no difference. Pin 6, definite difference, one side is shorted. Pin 7, little difference but not bad. Pin 8, pin 9, big difference there. So this is the left right, so two different puppies there. Pin 10, one side shorted, so that's reference, so left side, right side, left, right. Pin 11, identical. Pin 12, so that's reference. Well, we can't say reference, we can say left side, right side, because they're both bad chips. Pin 13, both shorted. Pin 14, both shorted. Pin 15, both shorted. Well, maybe not, just a little bit difference on 15 there. But both of these chips, neither one of them line up with a reference of a brand new one, so I know that both chips are bad. As we can see here, my little jigs kind of paid off. I was able to compare the brand new ICs to each other to verify, and then the old ICs to a reference new one, and then the old ICs against each other, and they all turn out to be slightly different. And I'm glad I made this little jigs, because that just verified kind of what I already knew, but verified it in a very seeable way. And these were robust, and they worked out. Maybe not the prettiest things, but they certainly got the job done. They told us what we need to know. So investigating further, maybe you don't have a curve tracer at home. Maybe you don't have a the ability to make something like this. Fine. There's other ways that you can go about it. If you can get these out of the circuit, to be sure, you can test them with just a multimeter. So we'll just do that quickly here, and I'll show you just at least what the faults are of these particular chips. So if we just go on to ohm settings here, let's look at a brand new chip, and that's a brand new one. We'll take the left chip first. So I'm going to do it this way. So this is our brand new chip, and this is the left chip out of the amp. I'm going to put my positive lead on here, and we know one is ground, so we're going to get 400.K on pin 1, and here a little bit roughly the same. Pin 2, again the good one, 411. Pin 2, 403 roughly. Pin 3, 418. Pin 3, 409 roughly. Pin 5, or pin 4 rather, 411. Pin 4, 402. Pin 5, pin 5. Pin 6, pin 6. Look at that. So let's go back to pin 6. Here's the good, the brand new IC, 408K, and the bad one, 9K. So that's a big difference. See that? All right, let's move on. Pin 7, 352. Pin 7, 43 ohms. 43 ohms. Pin 7 on the new one is 352K. So let's go to pin 8 on the new one. Wait. Yeah, we knew that was going to be low ohms, 0.5. Pin 8 here. All right, that's identical. Pin 9. Pin 9. Okay. Pin 10. All right. Pin 10. A little bit low there. 350 ohms on pin 10 on the bad one. And then on pin 10, 403K. See the difference there? It's 403 kilo ohms on pin 10 on the new one. And on the bad one, on pin 10, we have 350 ohms. All right, moving on. Pin 11, 404K. Pin 11, 42 ohms. Look at that. Pin, where am I at? 12. Should be 1, 2, 3, 4, 5, 6. Pin 12, 433 on the good one. Pin 12, 426, so roughly okay, that's good. Pin 13, 315K. Pin 13, 60 ohms on the bad one. Pin 14, 413K. Pin 14, 215 ohms. Look at that. Pin 15. Oops. 445K. Pin 15. 2K. Some obvious differences. All right, and now on to an extremely important part of this process. And that is getting the circuit board to be able to be mounted back in position where it was at, or roughly about, and then also have these be in place with pressure on them back to the heat sink, and have them be soldered with no pressure on the pins. Why is that important? It's important because this is going to be in a guitar amp, and in a guitar amp there are all kinds of vibrations. This head will be sitting on a speaker cabinet, which could have 1, 2, up to 4 speakers or more, depending on somebody's setup, vibrating. You've got to imagine at its top capability, which is 100 watts, which is a lot of power. So anything that can break a solder joint will break if it has pressure on it when you initially put it in. So you don't want to do that. So you want to have a good balance. How do you achieve that balance? The very first thing for a setup like this is, if you don't have a jig, which is what the factory people would use when they put this board together and they put these ICs on. You have to simulate a jig. So how are we going to do that? We're going to use these heatsink as the jig. We're gonna mount these ICs and the circuit board all together without soldering anything first, because we're going to have cleaned up these pads so well that the ICs will just sink right in, and when we solder them, if we have to get to the back side, we can at least do the bottom 100% and then pull the board as needed, and then do any finishing touches on the top if we need. We shouldn't need if we're using flux, and if we're using flux the appropriate way. Flux should be able to pull the solder from one side to the other, as demonstrated before, even though I did heat both sides because this is a little heavy component and I want a little bit of more secure solder on there, but this is not required for these ICs. So the very first thing is we need to replace our non-conductive silicone. That's this guy right here. Now, one product that I like to use and have used with much success in the past is this guy. This is I'm not affiliated with these guys at all. This is Odyssey Thermal Pad, and the point is that it is 0.5 millimeters. General measurement as to where they were before. Kind of do the same thing here. Maybe try to get a little more accurate if possible. Yeah. Inch and 5/8. Inch and 5/8. And then you can see you want this part to rest on the rail. I'm going to turn that up. See that? So what I'm going to do here is I'm just going to make a little sliver like this, and I'm going to put this in between the bracket and that top of that resistor array on both sides here. See that? Slip that in there like this, and this way you're not touching. If you're really concerned that you might touch something on there, you can even double up on that like this. Put a little thicker cardboard in there, whatever, and put that down in there. I'll do that on both sides just since we're here. And use that as a gauge. And right now, I'm going to just line up the circuit board to make sure all the pins and those ICs are in there, and just barely put some pressure from both sides here. Make sure I'm not touching. Alright, so now that we have everything laid in there before we start soldering, the ICs are in the correct position, and they're looking pretty good left to right. I mean, overall the leads are all the way through. That's pretty nice. We've got our spacers in there, and we're not touching anything else electrical with those clamps. What we want to do is use a 9/64 inch-pound torque wrench. Now the guide says 12 inch-pounds. I only have a 10, but I think 10 is fine, especially with the higher level thermal pads that I'm using. We'll take a look. 10, 10, 10. Now I do have another torque wrench that I'll probably come back and put these at 12s later. Just I got to go find that. It's in the garage somewhere. And what I'll do is I'll go through and I'll add my flux to the top and bottom side, and I'll pull these pads out. These are no longer needed, these spacers here. And I'll go through and I will solder all those bottom pins. So since these are such fine ICs, as all ICs are, you know, you can toggle along and take care of them all, pin after pin. But when you have so many pins that are so close to each other, I think it's good practice to give them some cooling off time between solder joints. So what I like to do is I'll do one here. Make sure that puppy's good. And then I can take a heat sink, in this case just the tweezers. That's good. And then I'll come over to this one. Giving a little extra dwell time because I want that solder to get pulled through by the flux to the opposite side. And I'll let that one cool off, and then I'll come back over here. And etc., etc. And lastly, make sure that you successfully have your pads. If you use this particular style of soft pad, make sure that you have connection between the bodies. Of course, that's through the circuit board, but not through the body and the heatsink itself. I'm using the other side of the black anodized. So you can see that black anodized doesn't show, right? And this is, I'm using the thread here. You see that? For connection. So I know I got thread connection there. Now for sure I don't have connection, and I don't have connection there. But if you just try to go like this, you're not going to get the black anodized that's on there. Is not going to give you, it's going to block your conductivity. So you got to go into the screw housing here, the screw thread. So you can go screw thread to screw thread, screw thread to screw thread rather. Could even go here, but again, you got the black anodized in the way. You want to really be sure you go into the screw thread, and then housing, good to go, no connection.